Good afternoon, everyone. Sorry for the little delay there. All right, as soon as I get set up here. Okay, so a couple reminders, just that we have a quiz review session tonight to prepare for Thursday's quiz. I'm also holding special office hours that are just for asking questions on the material today in the lab from 4 to 6. You're welcome to come to either one of those. And of course, the quiz is on Thursday. So today, we're going to continue our discussion of how to improve the performance of our processors by taking a look at pipeline processors. So first, let's go ahead and define, what do we mean by the performance of our processor? So what we're trying to optimize is the amount of time that it takes for our programs to run. So to calculate that, there's basically a few terms that we have to take into consideration. The first is the number of instructions you have in your program. The second is the number of cycles it takes to execute each instruction. And the third is how long it takes to execute, how long it takes for each cycle. So if we want to try to reduce our total execution time, we have a few things that we can play with. So first thing we could consider is, well, can I reduce the number of instructions in my program? Well, the only way to do that would be to actually change my instruction set architecture and support some more complex instructions, which would lead to longer clock period. So we're not really going to consider that at all. So let's assume we're sticking to our current ISA. So then the two other things to look at are the number of cycles per instruction. Well, we've already built a single cycle processor, right? So we're working in a situation where our cycles per instruction, or we call it CPI, is 1. So we really can't do better than that until we move to having multiple processors running in parallel. So the thing that we really want to work on is the time per cycle. So if we can bring the cycle time down, then we're going to be able to bring the total time that it takes to run our program down, and our performance is inversely proportional to the amount of time it takes to run our program, so that would improve our performance. Okay, so let's quickly review, what has to happen in a single cycle in our machine. So a typical ALU instruction would follow a path that looks something like this. This yellow line right here is showing the first thing that happens is that we get the address of the next instruction from our program counter. That's passed to our instruction memory in order to fetch the next instruction. Once we have the instruction, we can decode it, and then we go ahead and read the source registers. We then use the values of those registers in order to perform some operation in our ALU, and then we take the result of that and write it back to our register file. Okay? Now, another path, though, which is longer, is if we also have to go through our memory. So this would happen in the case of a load operation. So for the most part, everything looks the same, except that now, after the execute, we've only computed the address of the location we're trying to access in memory, and so we pass that address to our memory. We basically do, a fetch or a load from our memory, and once we get the data back from memory, then we can write that back to our register file. So, of course, our clock period is going to be controlled by the longest path in our circuit, and so we have to account for this path that actually goes through memory as well. So what does our clock period look like? Well, our clock period is essentially the amount of time it takes to go fetch your instruction from the instruction memory, plus the amount of time it takes to decode the instruction, then the amount of time it takes to read the registers from the register file, the amount of time to do the execute in our ALU, the amount of time it takes to then fetch from our data memory, and finally, the amount of time that it takes to write back to our register file. So clearly putting all of these things together is going to be quite long, right? So we want to see what can we do in order to reduce this T clock. So what we're going to consider today is basically a pipelined implementation of the same processor. And we've already seen that when we pipeline things, we're able to lower our clock period, right? How is it that I lower my clock period when I pipeline things? I'm running fewer things in every single clock period, and so it takes me less time to do that, okay? And once we pipeline things, then the idea is that what's going to happen is my CPI is no longer going to be 1, in the sense that if, let's say, my pipeline processor has 5 stages, which is a typical classic pipeline structure that we're actually going to look at today. If it has 5 stages, then if I'm able to reduce my clock period by a factor of 5, then, you know, as far as my performance is concerned, the latency of actually executing any given instruction is 5 times that reduced clock period, and so I still end up being approximately equal. However, I'm able to, if I'm able to fill my pipeline and then execute 5 instructions all at the same time, then essentially I'm going to be completing 1 instruction per cycle, and so I'll be able to maintain a CPI of 1. Okay, so what happens in a classic 5-stage pipeline? Here are the stages. The first thing we have to do is we have to fetch our instruction. We call this the instruction fetch stage. And so this portion of our pipeline is going to maintain the value of the PC, and it's going to update it, and it's going to issue a request to our instruction memory. The next part of our pipeline is our decode logic. So our decode logic is going to receive the instruction that was provided from the instruction memory. It's going to decode that instruction, and it's going to also read the registers that are mentioned in the instruction that we will want to use in the execute stage. So the next stage after that is our execute, where we actually perform whatever operation it is we're trying to perform in our ALU. And then if it was a load operation, then what we produced in our ALU is just the address of the memory we're trying to access, in which case we pass that address to our data memory and we initiate a load from the data memory. If it's not a load operation, then we would simply pass the result from the execute down to the last stage, which is the write back stage. And the write back stage is where we write the result of either the load that came from memory or the result that came from our ALU back to our register file. Okay? So, so this looks pretty similar to what we discussed, you know, needs to happen in order to execute any given instruction. What have we done here? What we've done is we've split the execution of the instruction into 5 stages, and so basically each one of these boxes corresponds to 1 pipeline stage. And so clearly, if instead of having a T clock that has to be sufficiently large to do all of these things sequentially, I now am going to be limited by whichever one of these 5 portions is the slowest, and so my T clock is going to be measured as the maximum of one of those 5 stages. Okay? Everybody comfortable with that? Great. So by doing this, our hope is that we're going to be able to lower T clock, and thus without ultimately changing our CPI, so that we can ultimately improve our performance. Okay, so, well, you might say, all right, this sounds kind of easy. You know, here's my, I know already how to do pipelining, so here's my processor, and I just said I'm going to make a 5-stage pipeline, and so let me draw these 5, you know, contours, and looks pretty good, right? I mean, here's my, you know, first stage is my instruction fetch. It's giving the address of the instruction to the instruction memory. Then I get the instruction memory back, and now I do my decode and fetch my source registers. Then I'm going to go to my ALU. If it's a load instruction, I'll execute in stage 4, request to the memory, and finally in the last stage, I'm going to write back. So it seems like that's all we have to do, right? But Are there any problems with this? Any ideas? Well, it turns out that this isn't quite the same as the kind of circuits that we've learned how to pipeline so far. So far, we've only pipelined combinational circuits. This is not a combinational circuit. This is a circuit that has state, right? We have state in our program counter, we have state in our register file, we have state in our memories. So that's problem number one. Problem number two is that we have cycles in this circuit, right? If you take a close look here, we are taking our PC value and then feeding the next PC value back to our PC register. We are also reading from our register file, producing a value, and then writing back to our register file. So far, we don't actually have all the tools necessary in order to properly pipeline this circuit. And so that's what we're going to learn how to do today. All right, so what we've done here is we've taken this data path and we've just redrawn it so that it's easier to tell the 5 different stages, right? And so what I'm going to do here is a couple things. So there's a few simplifications in this drawing that I want to point out. So the first one is that for now, we're always going to assume that the PC is going to be incremented by 4. So for today, we're not going to be dealing with branches or jumps at all. We'll deal with that in Thursday's lecture. The second thing I want to point out is that I have 2 copies of the register file here. So this is just in order to indicate where the read from the register file happens and where the write from the register to the register file happens. So the read happens up here and the write happens down here, but we're actually talking about the same register file. And finally, we have our instruction and data memory, which for the time being, we're going to assume are magic memories. Does anybody remember what it means to be a magic memory? It's one cycle, but more than that, it's combinational. Okay, so our loads in a magic memory are combinational, so we actually get the result in the same cycle that we issued the request. Okay, so let's take a look at that. So right now, without any pipelining, I would expect my T clock to be the sum of, all of these operations that I need to perform. But what I'm going to do is I'm going to add pipeline registers between each of these stages. And so now you can, tell why we redrew this the circuit diagram the way we have. And so basically what we've got is we've divided up our work into our 5 stages. So up here I have my instruction fetch, then I decode the instruction that I got back from my instruction memory, then I read from the register file, and in the execute stage I use the values that I read from the register file to do something in the ALU. If it's a load, something from the ALU is my address to the data memory. If not, I just pass my result down to the next stage. And finally, in the next stage, I write back the result to the register file, where the result comes either from the output of the execute unit or from the output of the data memory. Okay? Everybody comfortable with this? Great. So what's going to happen here is that I've added these pipeline registers, right? So now my clock period is just going to be calculated by the slowest of these 5 stages. And each one of these stages is going to serve 1 instruction per cycle. So the idea is that when my pipeline is full, I'm actually servicing 5 different instructions at the same time. And we're going to take a look at how that works in a second. So our clock, once again, if we pipeline, goes back to just being the maximum of one of these 5 stages rather than the sum. Okay, so let's take a look at how this pipeline execution works. So I give you here a sequence of instructions, and if you recall from when we learned the combinational pipelining, we basically find it much easier to analyze what goes on in a pipeline circuit by using these pipeline diagrams. So what are these pipeline diagrams? The rows correspond to the pipeline stages. So we've got our 5 pipeline stages here, 1 per row. And the columns correspond to the cycles. And so this shows the execution of the instructions over time. And so what we expect to see in these pipeline diagrams is that an instruction enters in the instruction fetch stage, and then every cycle thereafter, it proceeds to the next pipeline stage. And so here we see the add I in cycle 1 is in the fetch stage, then it moves down in cycle 2 to the decode stage, and so on until by cycle 5 it makes it down to the write back stage, okay? And so we have this diagonal progression of our instructions through our pipeline. And the other thing that I want to point out is that if you look at what happens once, we've gotten to cycle 5, we're now actually processing 5 different instructions all at the same time, each of them being in a different stage of my pipeline, okay? So what's the point of all this? Well, the point of all this is to think about, how all of this is going to work and whether it's going to behave correctly. So the first thing we're going to ask ourselves is, when do the actual reads and writes happen in this pipeline processor? So can anyone tell me, from what we've seen so far, which is the stage in which I'm reading my registers? Yeah? Decode? Decode, that's right. And which is the stage that I'm writing my registers? My write back, exactly. So if I take a look at what that corresponds to in this pipeline diagram, I'm just going to look at the add I for this example. And so what I'm going to see is that in cycle 2, the add I is going to read its source register, which is register X10, but it's not going to write its return value to register X11 until the end of cycle 5. Okay? So let's keep that in mind. All right, so what is my CPI, or cycles per instruction, in this pipeline processor? So how many instructions does it take me to actually execute a single instruction? I have to go through 5 pipeline stages. So basically, if each stage takes 1 cycle, I would take 5 cycles in order to have one instruction go, from the beginning of my pipeline all the way till it's done being executed, right? And so my latency is 5 times t clock, but we said that our t clock is small because now it's just the maximum of whichever pipeline stage is the slowest controls the t clock. But what's more important here is our throughput. What's the throughput of this pipeline processor? How often are instructions being completed? Yeah?
Once every cycle.
Once every cycle, exactly. So my throughput is 1 per instruction per cycle, and so even though a single instruction takes 5 cycles to actually go from the input to the output of this pipeline processor, my CPI is back down to being 1. If this is assuming that everything works well and that I'm able to keep my pipeline full and actually outputting instructions once every cycle. Okay, well, of course, it turns out that things aren't quite that simple, and we're going to see what kind of problems actually arise. So before we do that, though, I want to change the model of our diagram just slightly to make it a little bit more realistic and more like what you're actually going to build in your design project. And so in the first slide I showed you, I said we were using magic memories. And here we're actually going to use clocked memories. So let's just first understand what's changed and what's the same. So for the most part, everything is the same about this circuit, right? So I have my pipeline registers, which are separating my 5 different stages of execution. I've got, each stage is servicing 1 instruction at a time. And for now, I'm still just dealing with PC always being incremented by 4, and so I'm not looking at controller branch instructions at all. But what's changed? What's changed is the diagram of these instruction memories. So if you recall, in the previous diagram, what I did was I had this register coming after the memory. And so basically the result of an instruction fetch was produced in the same cycle. Now, a more realistic model is that actually the read from memory is clocked. So I don't get my result until at least the next clock cycle. Okay, so what is that going to do to the timing of how this processor works? So first, let's just take a quick look to make sure we're all on the same page of what change we've actually made here, right? So this was my original picture where my register came after the memory. And so what the timing of that looks like is the following. So suppose that in the first cycle, I gave an address A0. After some propagation delay, but within the same clock cycle, I would get the data of the memory location whose address is A0. So I would get D0 in the same clock cycle, okay? That's what a magic memory does. A more realistic memory, however, looks like this. And so here what's happening is in my first clock cycle, I'm passing A0, but my result from my memory doesn't come back to me until the beginning of the next clock cycle, okay? So this is what we mean by having clocked reads. Okay, so this is good because at least it's a much more realistic model of memories, and it's also going to help us with pipelining. And so from here on out, we're going to work with this more realistic memory model. And for today, we're going to assume that that the memory always responds within one cycle. And next time, we're going to talk about what happens when that's not the case. Okay? All right, so does anything change in terms of the execution of these instructions with the modified memories? No, my pipeline diagram looks the same. The only thing that's different, right, is if my interpretation, let's say, of when I'm actually reading from memory. So if I take a look at the load, for example, I see that I'm reading the register for the load in the decode stage, just like I did before. But then I pass the address to the memory that I want to fetch at the beginning of cycle 5, and instead of getting my data back within cycle 5, I only get it back in cycle 6. Okay, but I'm getting it towards the beginning of cycle 6, and so I still have enough time to then take that value that I fetched from my memory and write it back to the register in my write back stage. And so effectively, things look the same here. I'm reading in the decode stage, and then I'm writing at the end of the write back stage. Okay? All right, terrific. So far so good. But if you looked carefully at the instructions that I showed you previously, they were each using different registers. So there were no dependencies between the instructions. In reality, that's not quite how things work, right? Generally, we want to use the results of whatever instruction we just executed in order to do something else with it. So if we look at this code sequence, we see a more realistic situation where the add-I is writing something to register X11, and the exclusive OR needs to read from X11, okay? So if, I filled my pipeline diagram just like I did before, would things work properly? No, right? Let's take a look at why not. Well, the exclusive OR is trying to read the value of X11 in cycle 3. But the updated value of X11 is not going to be written by the add-I until the end of cycle 5. So clearly something's not going to work quite right, and my exclusive OR is going to end up reading a stale value of X11 rather than the updated value. Okay? So That's not going to work. Clearly, our pipeline machine has to actually behave properly. And so we have to figure out, how do we deal with this problem? So this problem we call a data hazard, okay? Where if there are instructions in your pipeline dependent on each other, then there's what we call a data hazard between the two instructions. So how do we go about handling these hazards? So actually, first let me give you just a brief overview of how we're going to cover things. So as we've mentioned, pipelining tries to basically overlap a bunch of instructions that are executing at the same time. But now, because of the fact that the instructions that are executing at the same time might depend on each other, we have to deal with hazards, okay? And so we have two types of hazards that we want to deal with. The first is if the dependency is based on a data value. If it's based on a data value, we call those data hazards, and that's what we're going to be dealing with today. If, however, the dependency has to do with a program counter, then that's what we call control hazards, and that's what we're going to cover in Thursday's lecture. So basically, our plan of attack is, to figure out, we've already seen how we can have a pipeline processor that deals with completely independent instructions. Now we're going to learn, what do we have to modify in that pipeline processor so that it can also deal with data hazards. And then finally, on Thursday's lecture, we'll see what else we have to do to it to also handle control hazards. Okay. So how can we resolve hazards? There's basically three ways that we can try to resolve hazards. And the first strategy, which is the simplest, is just stalling. So what do I mean by stalling? It means that you wait for the result to be available by freezing your pipeline stages and keeping them from doing any useful work until the data that you're depending on is actually available to you. Okay? So we'll take a look in a minute at how that applies to our previous example. The second way that we can deal with data hazards is through a mechanism called bypassing. And the idea here is that what you're going to do is that as soon as your result is available somewhere in your data path, you're going to grab it from that location in the data path and pass it to the instruction that's needing it, rather than waiting all the way until the end of the write back stage in order to read it from the register file. And finally, the third mechanism is what we call speculate. And the way that this works is you basically take a guess at what the correct behavior is going to be, and you continue executing as if your guess was correct. And then eventually you find out, was your guess correct or not? If it was, then great, you went ahead and executed useful things. If it wasn't, then you have a little bit more work to do, because you have to undo any work that you did that shouldn't have been done. Okay? And that's what we're going to see really in Thursday's lecture. That's how we deal with control hazards. All right, so let's take a look at stalling first. So how do I resolve data hazards by stalling? So here's my same instruction sequence where my exclusive OR needs to read the value of X11, which is being written by my add I. All right? So what's going to happen is the following. If we draw out our pipeline diagram, what's going to happen is that when the exclusive OR enters the decode stage, it's going to say, hey, I need to read X11. Okay, but our processor knows that there's already an instruction that's currently in the pipeline that's going to write to X11. And so it's going to say, okay, I need to stall the pipeline. So what does it mean to stall the pipeline? It means that the exclusive OR is going to stay in the decode stage, and anything above it, so whatever was in the instruction fetch stage, is going to stay in the instruction fetch stage until that X11 value actually gets updated at the end of cycle 5. Okay? And so when we have these stalls, we have to fill our pipeline with something. And so what we do is we put in, we inject what we call no-op instructions. So no-op stands for no operation. So it's basically any instruction that's not going to affect our state in any way. Can anyone think of an example of what might be a no-op operation in our RISC-V? Yep. You could add immediate 0, but that's actually still going to update registers. Can you think of something even less invasive than that? I could just do an instruction that writes to register X0, which is always 0, and so effectively it doesn't write anything. Okay? So that's what a no-op looks like, and there's many possible implementations of the no-op. Okay, so, well, good. Now what's going to happen is that in cycle 6, my exclusive OR is finally going to be able to read the updated value of X11. And so from there, it's able to proceed down the pipeline and continue execution. All right? So now we're going to get correct behavior, but what's the problem with this? What happened to my CPI? It got much worse. Right? I'm no longer completing instructions at a rate of one instruction per cycle, right? So, so basically my CPI has increased, and so my pipelining isn't working quite as well as I would like it to. So we're going to consider an alternate solution. Oh, actually, sorry, before we get to the alternate solution, let's see what do we have to add to our hardware in order to actually support the stall logic. And so it's really fairly simple. Basically, we're going to have a new stall control signal, which basically is set to 1 whenever there is an instruction in the decode stage that wants to read a register that some instructions that's further down in the pipeline stage is going to write to. Okay? So if that situation arises, you set stall to 1. And what does setting stall to 1 do? Well, it keeps the PC from being updated. It keeps this pipeline register between the instruction fetch and decode stage from being updated. So we do not move on to the next instruction. We keep whatever instruction is there. And the last thing that we do is that we feed in no-ops to fill in the pipeline while we're doing the stall. Okay? Any questions about that? Great. So let's move on. Oh, actually, sorry. So there's one other thing that I wanted to point out. So in addition to having data hazards when you read and write the same register, I want to take a look at what happens if I execute, this sequence of instructions, which is a store followed by a load. Okay? If I take a look at the registers that I'm reading and writing here, they're all independent. They're all different. So you might say, no, there's no data dependence here. But what happens if it's the case that the value of the address that's being stored to in the store instruction, which is the contents of register 10 plus a constant 8, happens to be equal to the address of where I'm loading from, which is register 12 plus 4. Now I have a data dependency, right? I need to make sure that the load is actually going to read the new value that the store wrote rather than the old value, right? So just something to think about. But as far as today is concerned, this is not something we need to worry about because in our single cycle machine, our memory instructions complete in one cycle. And so basically, the store is going to be done in time for the load to read its new value. And here on this next slide, we can actually see that in the pipeline diagram. So imagine that we have these two instructions, and we do have a situation where both of the addresses are the same. What's going to happen here is that my store progresses through my pipeline, and at the beginning of cycle, so actually let me step back. In cycle 4, it feeds the address of the location it's going to store to the memory. and the store actually is clocked, and so it's done by the beginning of cycle 5. All right? Now, in cycle 5, the load has produced the address that it's trying to read, and so it's going to be able to read this updated value that the store just wrote, and thus, when it reads it at the beginning of cycle 6, it's definitely reading the updated value, and finally, it can continue as expected. So, assuming that our memory always responds within one cycle, this situation does not actually lead to any kind of hazard that we need to worry about. However, with real processors where that's not always the case, that's certainly something that we have to worry about. And so you either handle the situation in your pipeline stages themselves or in the main memory. All right, so now let's move on to a second way of handling data hazards. So we mentioned that the second way of handling things is by bypassing. So what's the advantage of bypassing? The advantage of bypassing over stalls is that we're able to get the data that we need faster than if we just wait until the previous instruction is completely done and has written its data back to the register file. So let's take a look once again at the same execution sequence where we've got a dependency between what the add-I is writing to X11 and the XOR is reading X11. And so now, what's going to happen is the following. Well, if I take a look at my execution of the add-I, at what point, which cycle have I actually computed the result of the add? I'm not asking when it's written back to the register file, but when am I done computing the result of the add? Yep. Yes, in the execute stage. Okay, so I actually could look at the value, the updated value that the add-I produced as early as the end of cycle 3. So if I use that information, then I can add an extra path here in my processor, which is called a bypass path. And so what am I doing here? I'm basically saying, for the XOR, when it wants to read register X11, instead of getting it from the register file, it's going to get it from this special bypass path that I just added to my pipeline processor. Okay? And so in that way, it's able to read the updated value of X11 sooner than, after cycle 5. Okay, so we're able to keep our pipeline full by using this bypass mechanism and thus reduce our CPI back down to 1. Okay, everybody see that? Great. So let's take a look once again at our hardware and what changes we need to make to it in order to support bypassing. So in red here, we see the logic that we had added for stalls. And now what we're doing is the following. We're basically taking the output of either the execute stage, which is shown here in blue, or the output of the memory stage, which is green, or the output of the write back stage, which is shown in yellow, and that's being fed into these large decoders that are added to our decode stage. Okay? And so what are those decoders doing? Based on what's going on in my pipeline, they're going to select whether I should read the register from the register file directly, or I should read it from one of these other locations in my data path. Okay? So how do I go about figuring this out? Well, basically, I'm going to bypass a value if there's ever a situation where in my stages that are after my decode, I'm writing to the register that I'm trying to read in my decode stage. Okay? Now, of course, if you're trying to, read X0, then we don't have to use this special bypass path because that's always 0, so you can special case the X0 case. And now let's also take a look at what happens if multiple instructions here, let's say my decode is trying to read X11 and both my execute and my write back are going to be writing to X11. Which version of X11 do I want? So let's, actually write an instruction sequence just to make sure we're all on the same page. And so let's say, I've got my exclusive OR, which is going to read x11, and let's say, I don't know, x0, and it's going to write to x12. And then up here, I've got an add-I, which writes to x11. And up here, I've got a move that writes to x11. And then in between, I do some subtract that writes to, I don't know, x4. So if I have this sequence of instructions, what's the value of x11 that I actually want to be reading over here? Is it the one from the add-I or from the move? It's the add-I, right? I want to take the most up-to-date value of x11. So imagine if I was executing this code sequentially, I would take the value that add-I produced and read that in when the exclusive OR runs. So what that means is that if I'm writing to x11 in both, let's say, the execute and the write back stage, I'm going to use the bypass path from the execute instead of the write back. So the one that is the latest instruction is the one that takes precedence. Okay? Any questions about that? All right, good. Okay, now bypassing is great because it helps us keep our pipeline full, but the problem with it is that it's expensive. So you might choose, instead of implementing all three of these bypass paths, it's perfectly reasonable to, let's say, implement just two of them. So suppose that instead of having all three, I got rid of this one that came from the memory. Then if I have a dependency on something that's in the memory stage, I can always use my stall logic to deal with that situation. Okay? And so you can use permutations of the stall logic together with this bypass logic in order to figure out what makes sense from a cost perspective and a performance perspective for your particular processor. Okay, well now let's go back to the fully bypassed implementation, and let's ask ourselves a question: if we have, a full bypassing, is there any need still for the stall logic in my processor? Can anyone think of a situation where I might still need to stall even if I have full bypassing? So what we saw is that the reason that bypassing worked for ALU instructions is because their result was ready as soon as the execute stage. But for which instruction is the result not ready by the execute stage? My load instructions, right? My load instructions have to go through the memory stage. And so let's take a look at what happens, if I have a data hazard that is associated with a load instruction. Okay, so here what I've got is I'm doing a load into register X11, and then the exclusive OR is reading register X11, and I have now a processor that has full bypassing, but what I'm claiming is I'm still going to need to stall in this situation. So let's take a look at why. So here's basically what our pipeline diagram looks like in this situation. So my load is proceeding through as expected, and my exclusive OR comes into the decode stage in cycle 3. But the result of the load is not available in cycle 3, right? So even though I have these bypass paths, I can't use them because they don't have the right result yet. So I still have to stall my pipeline until the load is at least in cycle 5. Right? Once it's in cycle 5, then at the beginning of cycle 5, the data memory has provided the result of that load, and so I still can go ahead and bypass from cycle 5 so that the exclusive OR can complete its decode in cycle 5. If I didn't have any bypassing, I would have to stall for yet one more cycle. Okay, and so this example is showing you that you actually need both stall logic in addition to bypass logic, even if you have full bypasses. However, the bypasses are still helping you gain one cycle in this example. Okay? All right. So the bypass path is basically showing that here, instead of having to wait to do the decode in cycle 6, we're doing a bypass from the load in the write-back stage to the decode in the, to the XOR in the decode stage. Okay, and so the XOR was able to go ahead and read X11 even before X11 got updated in the register file. All right, so just a couple last things before we finish off. So you can imagine that compilers might be helpful in order to try to find some situations where it could rearrange the instructions and the order in which they need to execute in order to reduce the dependencies, right? So if I look at this example over here, I see that I have a direct dependency from the load to the exclusive OR. However, my subtract and my exclusive OR I instructions are completely independent of the other two. And so I could have a compiler replace this instance, which we just saw requires 2 stalls plus bypassing, into code that looks like this. Okay, so what have I done here? I've just moved the exclusive OR instruction to come after the sub and the XOR I. Okay, so by moving it to come after, then by the time that the exclusive OR is in the decode stage, the bypass path is going to have the result of the load available. And so now I can go ahead and execute the sequence of instructions with no stalls. Okay, so we're going to go ahead and use our compilers in order to try to improve our performance as much as possible, but in reality it's actually pretty hard for compilers to find these kinds of optimizations, because it tends to be the case that we actually have many dependencies between our instructions. In addition, the other thing that we have to worry about is the size of our pipeline. So let's first quickly summarize. So in order to deal with data hazards, we said that the first strategy that we can follow is to stall the pipeline. So the advantages of this is that it's very simple to implement, but it increases our CPI the most. And so that's going to have an effect on our performance. Strategy 2 was bypassing. So here, as soon as the value that you're trying to fetch is available somewhere in your data path, you pass it to the decode stage. And so this is great because you're able to have your pipeline be more filled and thus lower your CPI, but of course it's more expensive because these are huge wires and very large multiplexers that we're adding to our pipeline processor in order to support bypass paths. And the last thing that I want to leave you with is the following, which is today we talked about a 5-stage pipeline, which had these 5 stages, but in reality, modern processors have many more than 5 stages in them. And so as you increase the depth of your pipelines, the amount of data hazards that you're going to run into is only going to grow. Okay, so the more pipeline stages we have, the larger the number of data dependencies. And so even though we're lowering T clock by making each stage have to do less work, we're actually going to increase our CPI because of the data dependencies. Okay, and so this is something that's constantly being analyzed in the decision of how to pipeline our modern processors to figure out what's the right trade-off between the number of pipeline stages and the amount of data hazards that come about as a result of that, and which ultimately increase our CPI and make the fact that we pipelined it more not be as effective. Okay, so we're going to stop there for today, and next time we're going to talk about control hazards. Thank you very much.